Good afternoon. Um, I just I have another clipping. So there's some interest. Maybe I won't read it. I'll just quote from it. It's how many people know the periodic table of the elements? Okay, all right. I don't. Okay, I guess I don't mean know it to recite it, but you know, there's a method. There's a pattern, right? How many people know the pattern? Okay, good. Yeah, but yeah, all right. But apparently the pattern has now been exhausted. That the last with um, element number atomic uh, atomic number no, atomic number 118. Yeah. Okay. Um, that's like saying p a pin number, right? Okay. But you can't read stop it. You can't read. After with element number 118, which is named after a living scientist who's looking for the next one. It's named after Yuri Oganessian. By the way, one of the points of this article is that this joint effort, like the International Space Station, it's a collaboration of different countries, and one of them is Russia, and that seems to be on hold at the moment. But so the people in different places are pursuing the goal more independently than before. But the idea is that number 19, this guy Oganessian. Anyone know what number 118 is? Anyone know what the name of it is? Yeah, well, it's very similar. Yeah, it's with a small o, lowercase o. It's Oganessian. Yeah. Okay, but apparently number 118 completes the last shell. That's what it's called, like electron stable level. And so who knows what's going to happen with the next one? One guess is that they will not be unstable anymore. Maybe they will last for a long time. Okay. Anyway, that's this is in the Financial Times from a couple of days ago. So one of them is very unstable. Nihonium number 113. Anyone know where nihonium was discovered? Yeah, yeah. I mean, you have to, if you know a little Japanese, then the name for the country is Nihon, right? Yeah. Okay. And so the oh, okay. So by the way, it's note at the end of the article that this is not just fooling around. As this year's Nobel Prize for Chemistry, awarded for quantum dots, shows, the most rarefied pursuits can end up being useful. Okay. I mean, who knew that splitting the atom in 1939 was going to have consequences? Well, the quantum dots are these nanoparticles are now used in television sets, LED screens, and to eliminate tumor tissue for surgeons. But exploration also matters for its own sake. If an unmapped land of exotic chemistry lies over the horizon, we must surely set sail. one thing I was um, one thing I was trying to talk about today doesn't sound like K-theory and C-square algebras to begin with. So it starts off again talking about for the former Soviet Union. We're talking about one of the main constituents of which was Russia. All right. So as everyone knows, Russia suffered, the Soviet Union ran into economic difficulties some time years ago. And well, by the way, it's a smooth function, and it has all kinds of derivatives, right? It has all kinds of derivatives. And if the derivative is positive, that means it's facing up, right? And if the derivative is, but if the second derivative is negative, that means that it's going to start facing up more or less and less, right? Okay. Well, there's an article in the Mathematical Intelligencer from the late 80s, no, the early 90s, after the class. Okay, and but by the well-known, famous Russian mathematician Vladimir Arnold, and in this article I read that all mathematicians in the Soviet Union knew it was over, it was heading for a fall, because all the higher order derivatives were negative. Okay, well, this is for a function defined on the whole real line. If you have a function just defined on the integers, you can still talk about the derivatives, right? The discrete derivatives, sometimes called differences. You know, I forget exactly what they're called, the higher order ones. But the Laplacian, so on. We talk about all the higher order differences. And so if they're if you have a discrete times and some quantity which it may be increasing at the moment, but for recent history might be level or increasing, but if the higher order derivatives are negative, then you know it's not going to be increasing for much longer. Well, okay. Well, what comes up with it's not exactly C-square algebra theory. I've been making it part of this C-square algebra course. Pascal's triangle, right? If you look at Pascal's triangle, then this is a way of testing whether what the higher order derivatives are, what the higher order discrete derivatives are. And we'll look at Pascal's triangle. Start with 1. Zero. All right. Okay. Well, because of the 451 step between consecutive points, consecutive adjacent points, it's natural to say if you look at what the natural way to fill in the number here. Okay, the natural way to fill in the number in the second split position in the second row is you make the sum of the rows add up to 1. Okay? That says what this number should be. And then in the next row, and you look at the first element, which is the first point, which has a number already attached to it. That's the idea. These are this is the quantity, okay? But by the way, this one is the difference between those two, right? Or it's this one minus that one. So it's but it's the difference. And this one then would be this one minus this one, right? Because the sum of these two is equal to that. In a Bradley diagram, it's natural to look at numbers which are related this way. The diagram is very simple. Pointing in one row, the 2 points below it. Then what that's doing, if you look at the numbers, so this is the original discrete sequence of numbers. Then the second diagonal sloping line next to the first one, this is the first order differences, right? Then the next row is the second order difference. And so saying they're all positive just means that we can fill in this diagram. We fill in the whole diagram with positive numbers, such that the sum of any two adjacent ones at any stage is equal to the preceding one. So here's a way of representing diagrammatically the higher order differences, and saying that they're positive. Saying they're positive is actually quite interpreted in terms of the Bradley diagram and the associated order group. So there's a single positive number A0 or a single positive number 1 on so you think of all these points as just being representing popular events. What a group is. But a number there, a real number, it gives you a linear functional on Z, right? So the number, the linear functional on Z coming from the number 1, it's just takes the number n, goes to the number n. And if you look at the number A0, the functional on Z, it takes the number 1 into A0, it takes the number n into n times A0. You have linear functionals at every stage. And they're furthermore what are called positive linear functionals, because if the numbers are positive, then the number 1 has a positive value. So all positive integers have positive values on the function. Okay. So we're looking at positive functionals on the order group. This compatibility condition says the functional at this stage tends the functional at this stage. Okay, so look at this group element, the generator of Z. You map it down to here. It's the sum of these two. Well, the value of the functional, overall functional, numbers for the generators at every stage. It goes into 1, 1. So the functional on that is the value, the sum of the values of the two points, the sum of the numbers of the 2 points, the sum of the real numbers. And that's positive, right? That's a positive functional on the positive elements of the order group. And this functional, and by the way, the sum of the values here is equal to this, so which is the value of the functional at this stage on this group element. At this stage, this is an inclusion. This represents an inclusion. And at this stage, the functional definition of these numbers, by the choice of these numbers, the functional at this stage agrees with the functional preceding. Okay, so we have a functional defined on the limit, the limit order group. Positive functional on the order group. Real positive real value function, additive function. All right, well, what's the significance of this? Well, Has anyone heard of the name Hausdorff in any other connection than college? Okay, in what connection? Sadek, you've heard of it too? Sorry? So in what connection have you heard the name Hausdorff besides the Hausdorff topological space? All right, okay. Well, I was going to say except for Hausdorff dimension too. No. That's a very important concept, okay? But it's just he was such a he did a number of things, and I don't think what I'm thinking about now is related to Hausdorff dimension either. Okay. Chikam, what were you going to? Okay. Well, sure, no, that's good. That's good. I mean, Hausdorff dimension is not an elementary concept that everyone is familiar with. So. How many people are familiar with Hausdorff dimension? Okay, so that turns out it's just 3 people, and so I got 2 of them right off. Okay, that's very good. Well, no, maybe more. Sure. Okay, but now there's something else. It comes up in measure theory. There's something called the Hausdorff moment problem. How many? Suppose you look at a vague measure on the unit interval, okay, and you have some. You look at you can integrate functions on the unit interval, for instance, continuous functions. Then if you look at particularly you can integrate polynomials, and if you look at the constant polynomial 1, and you integrate that, and that sort of that's something called the total weight of the measure. Okay, that's the measure of the whole space. Normalizing the big measure. 0, 1, 4. That's the normal normalization. So, and if it's the polynomial x, function x of x equals x, then what's the moment? Did someone say a number? If you integrate x from 0 to 1, we don't have to. I don't have to know this. I mean, it's not. Yes, but did someone say something? Maybe the answer I would guess 1/2. If I didn't, sorry? If I had to guess without thinking, I would say 1/2. How many people would agree? Without thinking? Okay. All right. Maybe because I guess you sometimes know these things. Okay. So the point is that for moments are the powers of x, right? I mean the integrals are the powers of x for a measure. And any measure, well, if a measure is positive, that means the integral is positive. Or a positive function. If the integral is positive, then you can call that a positive measure. Of course, we talk about the measures of sets. It's the same as saying the measure of a set is positive. Well, what Hausdorff, well, there was a problem. I guess it was raised by Hausdorff. Maybe he solved it too. How do you tell? What's a good way of telling if a sequence of numbers, positive numbers? How do you tell whether it's the moment sequence or a positive measure? Okay. Well, the answer is not quite a proof. It's not a proof. The proof will involve the order group. Okay? The proof will involve the order group. Or a proof, not Hausdorff proof. But the answer is that the higher order derivatives should all be positive as well. Okay. Not only are the numbers positive, the 0th order derivatives, you might say, but the 1st order derivatives, which are the differences, is not going to be a decrease in sequence. That makes sense, right? X squared is less than or equal to x on the interval 0 to 1. So it's going to have a smaller interval, right? And so it's obviously a decreasing sequence. So that means this second sloping row is going to be positive numbers. But, well, yeah, I guess we're going to have to think a bit to prove that if you have if you look at the moments, then the higher order are also positive. But Hausdorff's answer was that was exactly the condition. If you had a sequence of numbers, such as the zeroth order of derivatives are positive, the first order derivatives are positive, the second order derivatives are positive, all orders derivatives of higher order differences, which are all positive, then this sequence of functions is off to the races. It comes from the measure. Okay. But by the way, I don't know if I said something about this diagram. Just forget about the functional. Just look at the diagram and the z's. Okay. An ordered group. You get an ordered group. This ordered group. Suppose this ordered group were just continuous functions on the interval 0, 1. And a positive functional on that would be already a measure, already be a positive measure. That's in France, I believe that's how they define a measure. Okay, the positive the measure on 0, 1 is a positive linear functional on the ordered vector space and functional, continuous real valued function on the interval 0, 1. And in this country, I guess it's true. If you have a measure, positive measure, then it gives you a positive linear functional. So that's pretty easy, I guess. Positive measure of the integral is positive. Conversely, if you have a positive linear functional on the vector space of continuous linear functions, continuous real value function, then it's just integration with respect to some positive measure on the interval. Okay. Well, if this order group were just continuous functions on the pointwise order, positivity meaning if something is just positive as a function, then it would be finished, right? Hausdorff's problem is a new proof. Well, assuming we could prove that the order group was just continuous functions on the in such a way that doesn't have too much have to be a natural way if these such that the order structure isomorphic in such a way that the order structure coincides with the order structure in the gravity diagram. Oh wait, well, this can't be true. It can't be quite true, right? That if you look at continuous functions on interval 0, 1, how many are there? Richard? Well, all right. But I was going to, I mean, there are infinite many integers too. And these ordered groups have infinite many elements. Okay. But I wanted to be able to say that the nevertheless, even though they're both infinite numbers, the number of elements in the ordered group and the number of continuous functions are different. Are we familiar with terms that say that different infinite numbers are in fact different? Well, we've been talking recently about that. Okay, so in other words, this order group can't be just continuous functions. It can't be all continuous functions on the interval 0, 1. But in fact, it's isomorphic to a dense subgroup of continuous continuous functions on the interval 0, 1 in such a way that it's in an order-preserving way. Well, an order-preserving way, if you define the order relation on the interval, the continuous function on the interval, this is maybe the function x times 1 minus x. You want to restrict the positive in the interior, okay? Because that's what you get, okay? You look, it turns out that these group elements in a natural way can be thought of as polynomials with integral coefficients, okay? And the order relation is exactly strictly positive, strictly greater than 0 on the open interval. So it implies greater than or equal to 0 on the closed interval. That's not the same thing. So just so that's a slightly I mean that's a minor point. And it's not just ordinary pointwise order, but that doesn't matter. It doesn't matter, okay? Because if you take continuous functions on the interval 0, 1, take all continuous functions on the interval 0, 1 with this order, then also the positive functionals, positive real value functionals will be exactly the same as the ones that are pointwise positive. Next example. Okay, so in other words, even if the order relation on polynomials we take to be a slightly unusual order, we don't require it's polynomial, it's continuous functions on the closed interval, okay? Continuous functions on the closed interval. Positive on the interior, okay? So that's the order relation. That's the vector space of some continuous functions. And if you look at the polynomial over integral coefficients, go on. And square brackets x. Okay. Well, this is actually, it's not going to be dense. It's not going to be dense because the values at the end, the values of the 1 will be just integers. Right? And that can't be dense in arbitrary continuous functions. Suppose you take suppose you take this, suppose you take q instead of z. Take q instead of z. What is group 2? Okay. And then in that case, we take q of z. Q of x, q of x, the polynomials with rational coefficients. We can take real coefficients for that matter. Even to take real coefficients, that's now uncountable, but still it's not the group is only going to be polynomials. The reason it's polynomials, well, this is an exercise, okay? It's an exercise that I'm not going to do everything today, okay? But it's an exercise. If you look at the pattern diagram, which is Pascal's triangle, and you interpret it either with z's everywhere or q's everywhere, and it's polynomials in a natural way, and it's isomorphic. The ordered group is isomorphic to polynomials with coefficients either in z or q, depending on what you've taken. Okay. Basic finite state group. And it's isomorphic in such a way that the order relation on polynomials is this. And if you did say q, then what you got is a dense subgroup of continuous functions. And a positive function. So positive function will be continuous in the Q norm with respect to this order relation. And so then to the closure, which is everything, all continuous functions. And so if you're French, then you have a measure. Whereas in this country, most places, it's a theorem to have a measure. Okay. One of the two theorems which are called the representation theorem. What's the other one? Anyone? Rishi, do you have a comment, or you're just thinking from your illegal model? Well, okay. Well, there's even one theorem that has two Reese's in it. It's called the F and M Reese theorem. Okay. In this case, it's two terms from one of the two Reeses. It's an exercise to locate which one. Okay. Well, all right. And that's an exercise to locate the polynomials. Okay. But, well-defined problem. Of course, if it were just, if you look at the group itself, just forget about the order relation and look at the group, the z's, you can build on z. The next group is going to be countable, not only countable, but it's going to be isomorphic. It's going to be a free abelian group. It's a direct sum of, it's isomorphic to the direct sum of countably many copies of z. And any such group, well, that group is, of course, it's isomorphic to the group of polynomials with integral coefficients. Group isomorphism, that's trivial. Okay, that's that isomorphism doesn't necessarily well. You have to say what the basis is. If you take a suitable, the idea is to take a suitable basis here over z, suitable z basis, suitable set of generators, independent generators generate the group. And then if you consider those as modules, then group isomorphism also preserves, it takes the order relation we're talking about here, the polynomial, the order relation coming from the diagram for the inductive limit order group. So the question is, what's the natural basis for the inductive limit group? Forget about the order structure, maybe, and just wonder what the natural basis is. What the natural basis is for the. Anyone want to make suggestions? Well, okay, that's a good. That sounds good, but I don't quite follow it because there are a lot. So you meant the sloping lines going from the top right to the towards the lower left. Okay. But that's but how do you associate those with elements of the group? When we're talking about a basis, we're talking about elements of the limit group, right? Now, this is an increase. These maps are injective. It's pretty easy to see that these maps to the next are injective between the groups, okay? And so it's an increasing sequence of finitely generated groups. So every element in the limit comes from some finite state. That means you have to choose a bunch of elements, single elements from the different finite stages. Okay, but just don't say that. Don't tell me the whole story. Just tell me what the elements are. What is the group elements you take? What's the first one? Well, it's not a constant. It's just a label. It's a generator of the first z. In this context, yeah. Okay. So this is an element of this group, or the number one is an element of this group, and therefore, actually, I'm sorry, I'm interpreting the number one as a real number and also as an element of z. This point in the diagram can be thought of as representing an element of the limit group, right? And so you're taking that as basis element number one. It's non-zero, so we can take it as basis element number one. Okay. And what are you going to take for number two? Basis element number two. Okay, you're giving me more than just number two. I guess. Basis element number two, natural basis element number two for the limit group should be a single element. It should come from some finite state, presumably from level 2. So which I'm asking you to pick out some element from level 2. Did you say the right one? Well, it's got to be. It should be the right one. Maybe anyone is the right one. Okay, but except if you want it to correspond to you want it to correspond to squared, then I think there's a clue when we thought of these as the moments of the measure, because the this is the moment. If the number 1 is the 0th moment, and that's the integral of x to the 0, which is corresponding to the 1. But then a0, this is the first moment. I guess I should have called it a1. Well, that's that's what's the definition of the first moment? We integrate x, right? But somehow the polynomial x is associated with this point. We're looking for we'd like to have basis elements that correspond to monomials, right? So maybe the best guess if you want to take this point here to the second nice basis number, to the second nice basis element. Right? So now I suppose that this one will work, except this is supposed to correspond to x. This one would correspond then to 1 minus x. But that's I mean, look at polynomials. There are many different bases. If you take, but the monomials would be the simplest basis, right? Instead of x, you could take 1 minus x. But, that's getting a little complicated. So I think the simplest choice of basis for the group would be just, you're right, talking about a sloping line, the diagonal. But just take the ones that sit in that sort of prominent position, salient position. Okay, well that's what I would do, given that I studied the problem. Okay, and no, but I mean, I think that if you take that association, then the elements do generate the group. They form the basis for the group. And if you look at the correspondence that gives you between the group element, the group and the polynomial group of polynomials in the integer coefficients, then that will preserve it will give you the right, preserve the order. One thing will be positive in the order of the group, or you'll have an element of the limit group being positive if the element of the corresponding polynomial is positive in the sense that we're talking about, strictly positive at each point in the interior. Even though we haven't really seen how the interval 0, 1 corresponds to this picture. Well, actually we have, because if you look at what are the possibilities for A1? A1 is something such that 1 minus A1 is positive. A1 is positive, and 1 minus A1 is positive. That means A1 is a point in the unit interval. Okay, so there's where the unit interval comes in. Everything has, all right, but I think I've let so much of the cat out of the bag. It's not going to be very true anymore. Everyone knows the cats like going into bags, right? So that's not difficult. Everyone's seen the problem about hunting the lion. So how do you catch a lion? Well, a lot of different ways. That I've seen there's a story about it in an article. It's a semi-serious article, mathematical article, so it's not only math. the one of them is the projective geometry. You build a circular fence, a large circular fence, okay? And then you, well, no, it doesn't have to be large. It doesn't have to be large. In fact, you, in fact, it shouldn't be too large because you want to be sure there's no line inside the fence. You build a circular fence, and then you get inside, and you invert. Okay, but okay, that's one thing I want to talk about today. How much time do we have? What's another thing? Well, a lot of things we have to talk about, right? Some of them are, well, they're all. I think they're all. I think a lot of important things we want to talk about. Anything that C-theory and C-star algebras, and by the way, this of course is a limit order group. It's the K-theory, it's the K0 group of the C-star algebra, right? C-star algebra can be described in terms of the Glim algebra, the subalgebra of the Glim algebra. How do you write this algebra as a subalgebra of this? Well, just this point correspond to that point. Now matrix algebra, okay? You make this point correspond to that point, and then this, so this is a we take 1 plus 2. That's the diagram for that's the simplest diagram. So this is a 2 by 2. This is M2. This number. And the next stage is M2. And what's the next stage? Well, it's what's M4. Okay? 4. And so this stage, the algebra, the first stage here is the complex numbers, so that corresponds. Second stage is the direct sum of 2 copies of the complex numbers. Both points are 1 by 1. Okay, well that means it's a diagonal subalgebra, canonical diagonal subalgebra. That's obviously going to be compatible with this one. Now the next stage, well, M4, this one is M1 plus M2 plus M1. Okay. Well, I guess M4 has a block diagonal subalgebra, 1 by 1 in the upper left-hand corner, and the lower right-hand corner, and 2 by 2 in the middle. Okay. I'll bet you the natural map from here to there is compatible. Okay. As an exercise. So that means that you get this one in the subalgebra. Okay. And there's a way of describing it, the subalgebra without using the diagram. Also, that's a good exercise. When you just look at the infinite tensor product, and you pick out the subalgebra without using diagrams. Without looking at the inductive limit of these two, without looking at the inductive limit form of the two algebras. So, what are some of the other things I wanted to try to talk about sooner or later? Well, most of them we've started talking about. Well, one of them is lifting projections, okay? From the quotient. The ideal is AF. Quotient doesn't need to be AF. If the quotient is also AF, then lifting projections will allow you to prove that the big extension algebra is AF. It's always true if you have any C3 algebra with an AF ideal, complement finite dimensional ideal, then the vector projections lift from the quotient. And that's proved using the 6-term exact sequence of Watt periodicity, as it's called. It allows you to check that the K0 map from the big algebra to the quotient is surjective because you have exactness at the quotient, and the map from the quotient to the ideal K1 of the ideal is 0. The ideal is AF, and K1 of the complex numbers is 0 because the unitary group is connected. What's the unitary group of the complex numbers? So, Daniel, look at the C algebra of complex numbers. What's the unitary group? You're answering a different question. You're answering what is the K0 group, okay? Now, I'm not asking what the K1 group is, but I could, okay? So there are two questions. What's the K1 group of the complex numbers? And what's the unitary group? And those things are related because for C-star algebra, the K1 group, C-star algebra, K1 group is defined by looking at the unitary group and also for matrices and divided by the connected component. So if the unitary group is connected for every matrix algebra over the algebra, then the K1 group of the algebra is going to be 0. Okay? So that's why I asked you what the unitary group is for the complex numbers, because the next question would be, is it connected? But it's hard to say it's connected without saying what it is. Well, maybe it is. Suppose we talk about 10 by 10 matrices over the complex numbers. Can you prove that the unitary group is connected without describing it, without giving a description? So maybe the description is a red herring in the case of 1 by 1 matrices. But it's good to get a feeling for something. It's good to make it as concrete as possible, following Paul Helmholtz's dictum, right? That for every problem is an easier problem. Maybe this applies beyond this mathematics too. I wouldn't be surprised. But the trouble is, the easier problem might be hypothetical. So do you have any comments? In other words, you want to think about it. Okay, good. But that's how you can fill your exercise books with exercises, right? A lot of things pop up in class, and if they're later they pop up in your exercise book. Okay, so that's the AF algebra has 0 K1. So the map from the 0 of the quotient the ideal is 0, of course, because the codomain is 0. That means that the preceding map going from K0 of the whole algebra to K0 of the quotient is surjective. So that's what exactly it means, right? Exactly. So we have some object, an arrow going in and an arrow coming out. If that's exact, that situation is exact. That means the image is equal to the current. With everything, the image is surjective. That means the K0 element's left. That's a colloquial way of saying it, right? Surely, where there's smoke, there's fire. If the K0 element's left, it'd be surprising if the projections didn't lift. Well, in fact, they do. Okay? And the proof is kind of geometric proof, and it's due to Larry Brown, the one that said that so is K1. And I said, after he said what I was doing with K0, and I said so, he said so, there's also K1. This is what he had in mind. Beautiful. Think about it in the meantime, okay? How you go from lifting the K0 element. Now, K0 has positive elements, right? So if you have a projection in the quotient, then the K0 element is positive. Well, that comes from a K0 element upstairs. Well, if that were already positive, then you'd almost be in business, okay? It would be very close to, because that comes from a projection, and that projection is probably going to map down into the projection downstairs. At least they have the same K0 class. And if the algebra downstairs is AF, actually it's enough to look at the case that it's just finite dimensional. Okay? Even just C plus C, because you look at the subalgebra generated by the projection and the unit, and so that's if you have two projections that have the same K0 class, they're unitarily equivalent, and so the given projection will live. Okay, so if you could find a positive K0 element, it would be interesting. So remember that every K0 element is the formal difference of two positive ones. And furthermore, you can take the second one to be a multiple of the unit in some matrix algebra. Okay, okay, but think about that. Okay, well, it looks as if we have this room for another hour. I don't know how many. Well, not. Usually people would start to come in, but I don't know how many people are free. Oh, by the way, today's Friday, right? Okay. Well, there's another room that we have for an hour too. That's upstairs. That's well, yeah. Joshua Lau has room 6180. That would take just about everyone, I think. Not maybe not quite. Pretty well. If you don't mind standing for a while, it rotates. But now, this room is, but if this room is going to be permanently empty, maybe we could move things down here. Does that make sense? Of course, no room is ever permanently empty.